Hello, welcome back. This is still algorithmic game theory, and as a matter of fact, what we will be discussing today will be quite algorithmic. So where are we? Last time we introduced correlated and coarse-correlated equilibria, and then we also got to know these no-regret dynamics. But for these dynamics, the one missing piece was the algorithm that each player uses individually to choose which strategy to play next. And we then saw that this algorithm would have to fulfill a no-regret guarantee so that overall what the players are playing turns out to be a coarse-correlated equilibrium. And the only missing piece, as I was saying, is now how do these algorithms work? Let's once again recap what the problem statement is for such an algorithm, which we kind of introduced already last time. As we've seen, we will play this in capital T rounds. And in one of these rounds, the following happens. We have one player, and this player picks a probability distribution which we call PT, which is a vector P1 through P capital N over her strategies, and what is now capital N? Well, that's just the number of strategies. And then, after the player has picked this probability distribution, the adversary picks a cost vector which we call LT here. This assigns a cost value to each of the strategies, and these costs we now assume to be between 0 and 1. And then a strategy AT is drawn from PT. So according to the probability distribution PT, we now draw one of these strategies, and the player incurs cost L superscript T subscript AT and gets to know all of LT. So this is very different from all the games that we were considering so far in this class, because now we actually just have a player and an adversary. The player always chooses a probability distribution over her strategies, and then the adversary chooses a cost for each of these strategies. And then, only then, a strategy is drawn from the probability distribution, and this is then the cost that the player will incur. So it's really important to understand the order in which things are happening here, that the player has already committed to the probability distribution when the adversary is choosing the cost vector, but what the player has not yet committed to is the particular strategy. This is drawn from the probability distribution that the player committed to only afterwards. What is a good benchmark for such a setting? Well, the nicest thing for a benchmark would be the best action sequence in hindsight. And what would that benchmark be like? Well, take the sum over all time steps, and then always in every time step consider the action that had the minimal cost. This is what we would call the best action sequence in hindsight. But this would be far too strong as a benchmark, because what could happen here? For this example, to see what can go wrong here, we just have two strategies and an adversary that chooses LT to have a cost of 1 for the first action and of 0 for the other action if P1T is at least a half, and otherwise it will be the 0, 1 vector. Why that? Because the player will always put a probability mass on of at least a half on one of the two strategies, and the adversary already knows the probability mass that the player is putting on each of the strategies, so they can actually adapt to whatever we as the player chose there. So this might be one possible choice. And then, what would be the cost of the algorithm? The cost of the algorithm would be always, so we would now sum up the expectation of all these LT, AT, and in each of the steps we would now incur a cost in expectation of at least a half. So this would mean we would have an expected cost of a half times t for the algorithm, but at the same time this best action sequence in hindsight this has a cost of 0, because in every step there is an action of cost 0. Therefore, we'll do something that is slightly different, which we will use as our benchmark. this will be what we call the best fixed action in hindsight. So we swap the minimum and the sum so that you, for each strategy or action, you first ask what's this entire sum of costs throughout the entire sequence, and only then you take the minimum of the two. So this is not the best action sequence, but the best single action in hindsight. And we'll now write L min t as the expectation of this. Why is this still random? Well, because it depends on the random choices by the algorithm. It may depend on the random choices by the algorithm. And we'll compare our algorithm's expected cost, which we would get by summing up these LTAT values and taking the expectation to this L min t. The difference of the two we call external regret. This is, I hope, a definition that you remember from last time, and we've actually seen that it is enough to get to a course correlated equilibrium if actually this external regret grows sublinearly in time. And this is what we call a no regret algorithm. An algorithm is called no regret or no external regret if for any adversary and all t, the growth of this regret is bounded sublinearly in t. So this might, for example, mean that this r of t is bounded by some factors times square root t. And what the point is now is that if you just let this run long enough over time, then, well, you morally get closer and closer to the best single action with the cost that you incur. And this means that in these no regret dynamics, we get closer and closer to a course correlated equilibrium if all of these if all of the involved players play such a no regret strategy. By the way, it's not important how they do this. All we care about in terms of the last lecture is, well, we get this no regret guarantee some way. But they might even use different algorithms. Today we will be getting to know one specific algorithm, although there are many other algorithms which also give you this no regret guarantee. The algorithm that we're getting to know today is called the multiplicative weights algorithm, or you may also find this under the name hedge or randomized weighted majority. This is all more or less the same algorithm with maybe some tiny differences. We will certainly only scratch the surface when discussing these no regret algorithms. If you're interested in further details about all these no regret algorithms, you'll have to take my class on algorithms and uncertainty, where we cover these in much more detail. How does this multiplicative weights algorithm now look like? The algorithm now maintains a weight for each strategy, which we call WIT. WIT, this is the weight for strategy I in step T. And the probability that the algorithm uses, this depends on the weight. And let's just write down the algorithm. We'll have some learning rate eta, which we'll set later. So far, this may be just some arbitrary real number, which is strictly greater than 0, but at most a half. And now the algorithm does the following. Initially, we set all weights to 1. And then, in every step T, what we do is the following. We compute the sum of the weights. And let's call this WT. Then we'll choose strategy I with a probability PIT, which we now define to be small WIT divided by capital WT. And then we'll update the weights. Namely, we'll do a multiplicative weights update. This is where the name comes from. Namely, we take the weight we had so far and we multiply it with 1 minus eta to the power of LIT. Let's build some intuition of what this algorithm does. What do these weights mean? Well, the weights are just proportional to the probability that we use for a strategy in a step, or in other words, we always take PIT as what proportion the weight WIT has in the overall sum of the weights. And then we always update the weights. How do these weight updates work? They use this weird formula here. Where is this formula coming from? What would we have to do? If a strategy turned out to be bad, we would have to reduce the probability, and this is done by reducing the weight. If a strategy turned out to be good, then we shouldn't reduce the weight. Indeed, we never increase weights here, but we only, if a strategy turns out to be good, we just do not decrease its weight. And because the other strategies might be bad at the same time, their other weights will be decreased. How do they get decreased? Just suppose that LIT is equal to 1, which is the worst that can happen for a strategy, that it has cost 1. In this case, the weight is multiplied by 1 minus eta. If a strategy has cost 0, which is the best that can happen, then we'll multiply by 1 minus eta to the power of 0, so we'll multiply it by 1, which means we won't change it. And this 1 minus eta to the power of LIT just gives us something, well, continuous in between. You might also update this in a different way, and indeed there are equivalent ways to write this algorithm, or also, well, similar ways. You will find these in the literature. The important thing to understand here is if the costs turn out to be 0, do not change the weight. If the costs turn out to be 1, then change the weight by a factor of 1 minus eta, and in between do some continuous change. And what role does this eta have? What could we now choose for this eta? This eta might be, well, a half, for example. Or think of even a more extreme. Think of eta being 1. Then 1 minus eta would be 0. So as soon as any strategy had any cost, any non-zero cost, then immediately this term would be 0, so it would lose all its weight. A smaller value of eta isn't that extreme. So if you had eta only being a half, then, for example, a strategy whose cost is 1, you would decrease the weight still by a factor of a half. If now you turn down your eta to 0, then suddenly you wouldn't actually change any weights. This 1 minus eta would always be 1. So this is why this does not work for eta equals 0. The difficult choice that you have here is actually making this eta large enough so that you're aggressive enough in, well, decreasing the probabilities of strategies that turn out to be bad, and at the same time you don't want it to be too large, because it might turn out that a strategy is only bad, for example, at the very beginning, and you don't want it to lose it already this early in the sequence. For this algorithm, we can now show the following guarantee. The multiplicative weights algorithm for any choices by the adversary of cost vectors from 0, 1 guarantees now write L subscript MW for multiplicative weights and superscript T because we're considering T rounds. So this is the expected cost of this algorithm. This is at most 1 minus eta times the expected cost of the best single action in the sequence plus ln n over eta. And what we now see is that this guarantee depends on eta, and this is actually true for any choice of eta between 0 and a half. So one choice we might actually do is we might set eta to square root ln n over t, and then, well, just plug this in up here. We'll get L min plus eta times L min t plus ln n over eta. How big is this L min t at most? Well, it's at most t because no action ever has a cost of more than 1 in any step. So taking a sum over t steps will never give us more than t. So if we now do the math, we'll see, okay, this is L min plus eta times t plus ln n over eta. And n times t, this is actually square root ln n. And then we multiply this by capital T divided by square root capital T. And what's the other term that we're getting here? This is ln n times square root of t over ln n. And let's now see what this gives us. Well, we'll actually get twice the same term, namely square root of t times ln n. Which means we have a no-regret algorithm. Because what's the regret that we're getting here? This will be at most 2 times square root t times ln n. And this clearly grows sublinear for a fixed number of strategies. So if we are able to show this guarantee, then we definitely have a no-regret algorithm, which means all we have to do is proving this bound here. And this is exactly what we'll do next in 2 different steps, because what makes this a little annoying is that we have this adaptive adversary. So we'll first consider only an adversary which fixes everything in advance, and only then afterwards we'll discuss why anything should happen due to this adaptive adversary, or, well, more precisely, we'll say why nothing happens due to the adaptivity of this algorithm, of this adversary. As I was saying, the entire setting of this no regret learning becomes difficult, at least for me, because there is this adversary who can actually base their decision on what our algorithm chose as the probability distributions. As it turns out, this doesn't actually matter, but I think it's much harder to think about such a dynamic process where, well, we as the algorithm make a choice, then the adversary reacts to this, and then we again make a choice, the adversary reacts to this, and in between there are also random coin flips. So let's ignore this for the time being, and let's just assume, well, there is this adversary who fixes everything in advance. So first the adversary fixes everything, and then we run our algorithm, which means the adversary doesn't actually know what we are doing. This makes it much easier to argue about the regret of the algorithm, because, as I was saying, nothing changes dynamically by our random choices. Everything is actually predetermined. Everything that the adversary does is predetermined when we start. And we will now show the following proposition. We'll show that for every fixed non-adaptive sequence which I'll call L1 tilde through LT tilde of cost vectors from 0, 1, multiplicative weights guarantees that the expected sum of costs will be at most 1 minus eta times LIT plus ln n over eta. And I forgot the tildes here, so this is now, to distinguish this from our adaptive setting, I'm in all that we're doing now, I'm writing L tilde, so I'm writing small l tilde for what the adversary fixed in advance for a particular step, and capital L tilde, let's write that down, we'll have capital L tilde subscript I superscript t. This is the sum of the costs of the teeth strategy, and we'll have the cost of multiplicative weights, which we remember was this the sum of the L tilde subscript AT superscript T. But now this is much easier to write because the probabilities, those don't actually change. No, those aren't actually random variables. This might be a little mysterious if you hear this for the first time, but remember how the algorithm works. the algorithm, if what the adversary does is fixed, then let's go back to the algorithm. If the choices of the adversary are fixed, then also these weight updates are fixed. They have nothing to do with this random choice that happens in the second step here. This is predetermined by what the adversary does. And we're now assuming that the adversary isn't adaptive. So this means that also these PRT, those aren't random variables themselves. By what the adversary determines, these PRT are already determined. These AT, those are still random variables. But the nice thing is we can just write it like this, because in advance, before anything has started, we already know, because the adversary determined the cost vectors in advance, we already know the probability that one of these actions will actually be played later on. So let's now prove this proposition. To prove it, we analyze how the sum of the weights decreases over time. We'll have the sum of the weights after for step t plus 1, so after step t. This is, well, nothing surprising here. It is the sum of the weights. But how do we get to this sum of the weights? Okay, this is simply by the multiplicative weights formula. Next, we want to understand this 1 minus eta to the LIT term, and I brought a plot of this kind of a function. This is what it will look like. So this is for the example of eta being a half, but for other values of etas it will just look the same. So this red line is connecting the point 1 with 1 minus eta, and the orange line is actually the function that we're considering here. And indeed, this is a convex function in terms of this LIT tilde, which means that what we can see here, that this will always be at most 1 minus LIT tilde times eta. So we'll get now that the sum of the weights is at most the sum of all WIT times 1 minus LIT tilde times eta. And this we can rewrite as the sum of the WIT minus eta times the sum of the WIT times LIT tilde. What is this first thing? This is just the sum of the weights. And this Second thing, let's just write this once again, but we'll see, let's just replace WIT by PIT times WT. This means we now get WT times 1 minus eta times, take the sum over all strategies, PIT times LIT tilde. What's this? What's this sum here? We take the sum over all strategies and now the probability that we play this strategy times its cost. This is the expected cost of the algorithm in the step t. So let's write this with L subscript MW superscript T tilde. How does this now help us? Well, we now know from the sum of the weights after step t is at most the sum of the weights before step t times something. And we can now just repeatedly apply this bound. If we repeatedly apply this bound, then we'll get that the sum of the weights after the last step, which is capital W superscript capital T plus 1, this will be the initial sum of the weights times the following product. Take the product from 1 to capital T, 1 minus eta times this LMWT tilde. What's the initial sum of the weights? It is capital N because we have n strategies, each of which has an initial weight of 1. This is 1/2 of the proof, because we now see the final sum of the weights has something to do with the per step cost of the algorithm. And then we'll do another bound, which is that capital WT plus 1 will get a lower bound for this. This is the final sum of the weights. No weight will ever be negative, so this is at least the maximum of these weights. And for any fixed n, for any fixed I, how do I get the weight after step t? What I can simply do is I can just take the initial weight and then multiply this with all the weight updates. These weight updates are just happening. And I know how the weights will be updated because they depend on these L tilde vectors. Let's simplify this a bit. What's the initial weight? The initial weight is 1, so I can simply ignore this. And I can now write that this is at least 1 minus eta to the power of the sum of the LIT tilde. So this is nothing but 1 minus eta. 1 minus eta is smaller than 1, so I can write down the minimum here in the exponent of the sum of the lit tilde. Or I might also write this as 1 minus eta to the power of L min t tilde. What do I now have? I have an upper bound on the final sum of the weights that depends on the cost that the algorithm incurs, and I can compare this to via a lower bound to the cost of the best strategy. If I now combine the two, what do I get? I get that n times the product of 1 minus eta times L mw t tilde, that this is at least 1 minus eta times L min tilde t. Now I can take the logarithm on both sides. What I'll get is that ln n plus the sum of all t ln of 1 minus eta times ln mw of t is at least L min t times ln 1 minus eta. Now there's one more thing that we'll have to understand here, namely how do we now get rid of these logarithms. But fortunately, we can use the following bounds for the logarithm. We can see that this logarithm that we have here on the left hand side, we can upper bound by 1 minus eta times lmw t tilde, and this logarithm here on the right hand side we can upper bound by 1 minus eta times 1 minus eta squared. And if we now combine this, we'll get that ln n plus take the sum over all t minus eta times ln mw t tilde. This will be at least L min t tilde times 1 minus eta squared. Now divide by 1 minus eta and we'll get to the sum of all this L tilde t mw. This will be at most 1 minus eta 1 plus eta times L min t plus ln n over eta. And this is exactly the bound that we were claiming. And this is exactly the bound that we claimed. So I agree that when you see this for the first time, this might look a little mysterious. And I can only say it gets a little less mysterious over time. Over time, you'll realize, well, this also doesn't feel so strange why this works. But at the same time, why these calculations actually give you what you want, this is maybe still surprising, even when you're very experienced with these algorithms. But what was the general structure? That's at least what you should remember at this point. We were asking, how does the sum of the weights change? And we got a bound in terms of the best strategy, in terms of the cost of the best strategy, and we also got a bound in terms of the cost of the algorithm. Not exactly the cost of the algorithm, but rather this thing here. So this is, and then we derived at exactly this bound, because here in between there was the sum of the weights. And then you just do some calculus, some smart calculus, but then fortunately for us, we get to exactly the point where we want to get. But what we still haven't done so far is talking about the adaptivity of the adversary. And this is exactly what we will be doing next. So far we analyzed the algorithm only for a non-adaptive adversary, which means that the order is actually different than what we actually wanted it to be. So the order that we considered so far in our analysis was the adversary fixes all the cost vectors, and then our algorithm plays on these. But what we were actually asking was that the player chooses a vector of probabilities, then the adversary chooses one cost vector, then we draw one of the actions at random, then we choose another probability vector. The adversary may now, depending on what came out in the coin toss that determined the random strategy in the first step, they may now choose another cost vector, and then, well, again, there is some coin flipping to once again determine a random strategy. How do we do this? Well, fortunately for us, our guarantee that we have so far is just strong enough to also apply to this adaptive setting. Why is this true? Well, the general point is that the algorithm is somewhat deterministic. And you may not say, but there is this randomization that we always choose a random strategy. Yes, I agree. But this is not what I mean. What I mean is that the probabilities, those don't depend on these random choices. The probabilities, those aren't random variables. You could also picture a setting in which you adapt your probabilities depending on some random choices. But this is not what is happening here. So the adversary actually knows in advance how these probabilities will develop anyways. But let's try to formalize this. Our proposition is now that the multiplicative weights algorithm for any possibly adaptive choices by the adversary, of cost vectors from 0, 1 guarantees that its expected cost is at most 1 plus eta times the cost of the expected cost of the best single action plus ln n over eta. This proof now works as follows. We will now design an adaptive adversary that simulates, we will design a non-adaptive adversary that simulates the adaptive adversary by indeed anticipating what the algorithm will do anyway. So we'll design a non-adaptive adversary that simulates the adaptive adversary. How does it do that? We generate a random but non-adaptive sequence that we will now once again call with L1 tilde through L capital T tilde, which has the property that the expected cost of our algorithm with respect to this random but non-adaptive sequence is equal to the expected cost of the algorithm in the adaptive setting, and also that the expected best cost is equal to the expected best. Let's now understand these things. So if we get to this point, then we are done, because then we know, okay, for these we actually have the relation that we want. We already know that the regret is bounded with respect to a non-adaptive adversary, and because this non-adaptive adversary does everything that the adaptive adversary does, or at least causes the same cost, then we also have the bound for the adaptive adversary. So how do we do this? Let's first simplify this, the expected cost that the adaptive adversary causes our algorithm to have is the expectation of all these LT, AT. And we can now use linearity of expectation to say, okay, this is actually, instead of taking the sum of these random variables, and then taking the expectation, we might also take the expectation of each of these random variables individually, and then we take the sum. Why is this now, or what is it that makes everything difficult? Well, it's these strange random variables. These strange random variables, they depend on what the algorithm did up to this point, and also what the algorithm is doing right now. Why are they depending on what the algorithm did so far? Because the adversary is adaptive. Because the adversary may choose the cost of the actions depending on what we chose before. However, if we keep everything fixed that we've done so far, then there's only one more piece of randomization in here, namely it is the random draw that happens after the adversary chose the respective action, chose the respective cost vector. This means we can write this in a somewhat complicated way. So fix all the cost vectors before step t. And also fix all the actions before step t. This definitely fixes the probabilities, and now we just let the adversary react to this. This is true for any way we fix what happened so far, so we might as well get the unconditional expectation at this point by taking the expectation on both sides of this inequality, of this equality. And this means that we can write the expected cost of our algorithm simply also as take the sum over all steps. Now sum up these expectations and now let's use linearity of expectation again and see that we could also have this sum over all time steps inside the expectation. And this is now interesting. For which reason? Because here there's no AT even anymore. All we're talking about is the probability vectors. But those probability vectors, we already know what the algorithm, what these will look like. Because this is what I've been saying all along, that these probability vectors, those aren't random. Those don't depend on the random choices of the algorithm, but only by what the adversary is doing. What does this now mean? How do we construct our adversary which is non-adaptive? we construct our non-adaptive adversary as follows. So suppose there is this adaptive adversary that we may now ask, well, what would you be doing in this situation? And we just give it some, we just let it play this entire thing that is happening here. And we just compute some other actions, some other realizations of these AT, which are not the true AT, but other AT. More precisely, we do this as follows. We now want to determine this non-adaptive LT tilde. Let's compute at this point, because we've already, suppose we have already determined all the other L tilde vectors. We compute all the probabilities. Those are determined by L1 tilde through L minus 1 tilde. And then we draw some A tilde t from PT. Sorry, we draw an AT minus 1 from PT minus 1. And now we ask the adaptive adversary, what would you do? We then get LT tilde based on, well, on the one hand, this P1 through PT, and on the other hand, A1 tilde through AT minus 1 tilde, which are not the actual actions, but we replace whatever the adversaries, whatever the algorithm is really doing by this fake sequence. The important thing is now that we'll have that the best actions cost in expectation is equal to the best cost, because to do the expectation of the best cost. Why is this? Because it doesn't actually matter whether this is A tilde or the real A. What the algorithm does, what the adversary does, doesn't actually change. The more difficult thing is, what about the expected cost that our algorithm has on this non-adaptive sequence? There we will use that we can actually rewrite this in a way that doesn't even depend on the A vectors. The PIT, those will always be the same. And therefore, we will get that also these will be exactly the MWT. And so we derived at the kind of a guarantee that we wanted, namely we devised a way to construct a sequence which is random but non-adaptive, which, well, the idea is simply to anticipate everything that the adversary will do, and eventually, because there's only one thing that the adversary doesn't know, namely what action the algorithm will choose in this exact step, but this is all that matters for the cost in this step. And the rest can be get rid of by linearity of expectation. So I have to say at this point that I'm not super happy with this proof, and I'm still looking for a more intuitive argument why this works. Once again, let me repeat my earlier point that this algorithm I do not consider a fully randomized algorithm, but these PT vectors, those are deterministic. And so if we understand the algorithm as being deterministic in terms of the PT vectors and only seeing the randomization taking place after the PT vectors have already been determined, then somehow I hope you see that all this adaptivity doesn't make a big difference, because what does adaptivity help an adversary anyways? This only helps if the algorithm is not deterministic. So only if the algorithm is randomized in some way, it helps the adversary can do better if it is randomized. If it is adaptive. So this concludes our discussion of course-correlated equilibria and no-regret learning. I hope you have now an understanding what these correlated and course-correlated equilibria look like, and why it is actually quite reasonable to assume that players do play these, because I consider such a multiplicative weights algorithm to be something very natural that players might actually use to update their strategies. At the same time, there are many more no-regret learning algorithms. If you're interested in these without the game theoretic context, feel free to take my class on algorithms and uncertainty at a later point. What we will continue with in this class is the question how much we actually lose due to the strategic behavior. So now we've got to know multiple equilibrium concepts, and it was somehow always implicit that due to the strategic behavior, well, society loses something. The world would be a better place if nobody acted strategically. And this is exactly what we will be bounding in the next 2 lectures, and which we will then formalize in terms of the price of anarchy and the price of stability. Hope to see you then.